Hey everyone, welcome back to the Deep Dive. We're diving into the heart of circuits today, folks. If you've ever wondered how electronics really tick, well, you've come to the right place.
Yeah, we're breaking down those little components that make our gadgets go beep and boop.
That's right, we're talking about inductors and capacitors. Essential stuff.
Absolutely. And we've been poring over some really interesting educational resources, trying to distill the essence of what makes these elements so fascinating and, how they work together in circuits to make things happen.
So think of this as your cheat sheet to understanding these fundamental concepts, right?
Exactly. Let's get started.
All right, let's kick things off with the inductor. Now, what's the one key thing someone should know about an inductor?
It's all about resistance to change. But not just any change. It's specifically about resisting changes in the flow of electrical current.
Okay, so it's got a sort of stickiness when it comes to current. Can you unpack that a bit? What's happening inside an inductor that causes this?
Sure, so picture this. An inductor is basically a coil of wire. Sometimes it's wrapped around a core, which can be magnetic or non-magnetic, but the core idea is the coil.
So we're talking about a wire wound up like a spring, basically.
Exactly. Now, when electrical current flows through this coil, it creates a magnetic field around it.
Right, because moving charges create magnetic fields.
Exactly. And here's the kicker. When the current changes, so does the magnetic field. That changing magnetic field, in turn, induces a voltage in the coil itself.
So it's fighting back against the very change that's causing it. It's trying to keep things stable.
That's a great way to think about it. And this opposition to change is what we call inductance, and we measure it in henries. You'll see an inductance represented by the letter L in equations.
And in circuit diagrams, you'll usually see that coil symbol to represent an inductor.
Yeah.
So is there an equation that neatly captures this relationship between voltage and current in an inductor?
Yeah, absolutely. It's pretty straightforward. The voltage V across an inductor equals the inductance, L, multiplied by the rate of change of current. So it looks like this, V equals LD.
Okay, so voltage isn't just about the current itself, but about how quickly the current is changing.
You got it. Now, this equation uses what we call the passive sign convention, which just means we're defining the direction of current flow in a specific way to make the signs in our calculations work out nicely.
Right, so it's a bookkeeping thing to keep everything consistent. So what are the big takeaways from this equation? What does it tell us about how inductors behave in circuits?
There are two key things to remember. First, imagine you have a constant, steady current, like what you get from a battery, flowing through an ideal inductor. In that case, the rate of change of current is 0. Plug that into the equation, and you'll see that the voltage across the inductor is also 0.
So under a steady current, the inductor basically acts like a straight piece of wire, a short circuit.
Exactly. It's just letting the current flow through without any resistance.
That's counterintuitive, you know. A coil of wire behaving like it's not even there. What's the second key point?
Okay, the second thing is that the current through an inductor can't change instantaneously. If it would be infinitely large, which would require an infinite voltage, and that's not going to happen in the real world.
Right, because nothing in the physical world can change infinitely fast. So it's like the inductor has inertia when it comes to current. It resists being pushed around too quickly. And you mentioned arcsing, like when you switch off an inductive circuit.
Yeah, when you abruptly cut off the current flow, the inductor tries to keep that current going. Since the current can't stop immediately, it can actually jump the gap in the switch, creating a spark.
Wow. So the inductor's fighting back, trying to maintain that current flow, and we see it as a visible spark.
Precisely. Now, what if we wanted to figure out how the current in an inductor behaves if we know the voltage across it?
Well, the voltage-current relationship for the inductor gives us voltage based on current, right?
Mm.
But if we already knew the voltage, how would we find the current?
Right, we need to think about things a bit differently. We can use integration. The current, at any point in time, depends on the accumulation of the voltage over time, plus any initial current that might have been present in the inductor when we started looking at it.
So it's not just the present voltage that matters, it's the history of the voltage that shapes the current.
Exactly, and that initial current tells us something about how much energy was already stored in the inductor's magnetic field. Now, what about power and energy in an inductor?
Yeah, let's talk about that. How much energy can an inductor store, and how do we figure that out?
The power at any given moment is just the voltage times the current. We can plug in our voltage-current relationship for the inductor and see that power is also related to the rate of change of current. The energy stored in the inductor's magnetic field depends on the inductance in the square of the current.
Okay, so the more current flowing, the more energy stored. And what about when there's no current flowing?
Well, if the current is zero, then there's no energy stored in the magnetic field. And because inductors can only store energy, not create it, we call them passive circuit elements.
Okay, so they're like energy banks, but they can't generate their own funds. Let's make this more concrete. What happens if we apply a pulse of current to an inductor where the current changes over time? What will the voltage across the inductor look like in that scenario?
This is where it gets interesting. The voltage across the inductor won't simply mirror the shape of the current pulse. Instead, it's going to be proportional to how quickly the current is changing. And remember, voltage can change instantaneously in an ideal inductor, unlike current.
Okay, so it's all about the rate of change,
Hmm.
not just the value of the current itself. Now let's flip the script. What if we apply a voltage pulse to an inductor that initially has no current flowing through it?
Well, the current in the inductor will build up over time, depending on how the voltage changes. Even after the voltage pulse is gone, the current in an ideal inductor can continue to flow at a constant level.
That's a bit mind-bending. Why would the current persist even after the voltage source is removed?
Think about it like this. The voltage pulse has pushed some energy into the inductor's magnetic field. And in an ideal inductor with no resistance, that energy has nowhere to go. So the current keeps flowing, representing that stored energy.
It's like the inductor remembers that energy push and keeps the current going. So how do we tell if an inductor is storing energy or releasing it back to the circuit?
The power equation helps us here. When the power is positive, the inductor is absorbing energy and storing it in its magnetic field. When the power is negative, the inductor is returning that energy to the circuit.
So it's all about which way the energy is flowing. Positive power, energy in. Negative power, energy out.
Exactly. And as we discussed, a constant current flowing through an ideal inductor means that energy is stored and ready to be released if needed, even after the original voltage source is disconnected.
That's fascinating. Now let's move on to our next component, the capacitor. If the inductor is all about resisting changes in current, what's the capacitor's main job?
The capacitor is the opposite, in a way. Its primary role is to resist changes in voltage. And it does this by storing electrical charge.
Okay, so it's like a voltage stabilizer. What does a capacitor actually look like, though? How is it built?
Typically, a capacitor has two conductive plates separated by an insulating material called a dielectric.
So it's two plates with something in between that prevents current from flowing directly between them.
You got it. The dielectric prevents the direct flow of charge, but it allows opposite charges to build up on each plate when you apply a voltage across the capacitor.
Interesting. So unlike the inductor, which uses magnetic fields, the capacitor relies on electric fields.
Exactly. The separation of charges on those plates creates an electric field in the dielectric. And when the voltage across the capacitor changes, the electric field changes too. This change in the electric field results in something we call a displacement current.
A displacement current. That sounds a little mysterious.
It's basically a way to describe how a changing electric field in the dielectric affects the circuit connected to the capacitor. It behaves like a regular current flowing through the capacitor, even though there's no actual flow of charge through the dielectric itself.
Okay, so a changing voltage across the capacitor, even though it's insulated, can still cause a current to flow in the circuit. How do we measure this relationship between voltage and current for a capacitor?
We use something called capacitance, which we represent with the letter C and measure in farads. The circuit symbol for capacitor is usually two parallel lines.
Okay, so C for capacitance, measured in farads. What are some typical capacitance values we might see in circuits?
Well, 1 farad is actually a huge amount of capacitance. In real-world circuits, you're more likely to see microfarads, nanofarads, or even picofarads.
Right, so much smaller units. What's the equation that links voltage and current for a capacitor?
It's similar to the inductor equation. The current I flowing into or out of a capacitor equals the capacitance C multiplied by the rate of change of voltage, dV dt. So we have mito I equals C dV dt.
Again, we see that the rate of change is key here. It's not just the voltage itself that determines the current. So what are the key takeaways about capacitor behavior based on this equation?
There are two big things to remember. The first is that the voltage across a capacitor can't change instantly. If it did, dV dt would be infinitely large, which would require an infinite current to flow. That's not physically possible.
Right, so capacitors have a kind of stickiness when it comes to voltage, just like inductors have for current. They resist those sudden changes. What's the second important takeaway?
The second is that if you apply a constant DC voltage across an ideal capacitor, the current through the capacitor will eventually drop to zero.
So once things settle down, the capacitor acts like an open circuit, no current flowing through it.
Exactly. Now, what if we want to figure out the voltage across a capacitor if we know the current flowing through it?
Right, because the equation we have gives us current based on voltage. But what if we already knew the current and wanted to find the voltage?
Just like with the inductor, we can use integration to find the answer. The voltage at any time depends on the accumulation of the current over time, plus any initial voltage that might have been present on the capacitor when we started observing it.
Ah, so the capacitor's history also matters. Its past voltage influences its present state. Now, let's talk about power and energy for a capacitor. How much energy can a capacitor store, and how do we calculate that?
The power, like always, is just the product of voltage and current. We can substitute our capacitor equation to express power in terms of voltage and the rate of change of voltage. The energy stored in the capacitor's electric field is related to the capacitance and the square of the voltage.
Okay, so the higher the voltage, the more energy stored in the capacitor. And what if the voltage is zero?
Then there's no energy stored. And just like inductors, capacitors are passive elements. They can't create energy, only store it.
Got it. They're energy savers, not energy generators. Now, we saw a fascinating real-world application mentioned for capacitors. Multi-touch screens. Can you tell us more about how that works?
Sure, many multi-touch screens use a grid of tiny capacitors embedded within them. When you touch the screen, your finger, which is conductive, changes the capacitance at that specific point on the grid.
So my finger interacting with the screen alters the electrical properties of those tiny capacitors.
Exactly. And this change in capacitance causes a change in voltage, which the screen's electronics can detect. By monitoring these voltage changes across the grid, the device can figure out where you're touching and even how hard you're pressing.
That's really clever. Using a fundamental electrical component to enable such a sophisticated technology. Now, let's look at some capacitor scenarios. What happens if we apply a voltage pulse to a capacitor that initially has no voltage stored on it?
Well, the current flowing through the capacitor will depend on how quickly the voltage is changing. A rapid increase in voltage will result in a surge of current as the capacitor charges up. When the voltage is constant, even if it's high, the current will drop to zero.
So capacitors are like electrical sponges, soaking up charge when the voltage is rising.
And when the voltage starts to decrease, the current will flow in the opposite direction as the capacitor discharges. We can also analyze the power to understand when the capacitor is storing energy and when it's releasing it.
Right, because the power tells us the direction of energy flow.
Exactly. When the power is positive, the capacitor is storing energy. And if the voltage across an ideal capacitor eventually returns to zero, all of the stored energy will be released back to the circuit.
So a capacitor can store energy and then release it later, just like an inductor. What if we apply a current pulse to a capacitor instead of a voltage pulse? What happens then?
In that case, the current pulse will push charge onto the capacitor's plates. Even after the current stops, the voltage across the capacitor will remain.
Why does the voltage persist even though the current is gone?
Because the charge is trapped on the capacitor plates. In an ideal capacitor, there's no path for the charge to leak away, so the voltage remains constant, representing that stored energy.
Fascinating. It seems like inductors and capacitors have this kind of complementary behavior. One stores energy based on current, the other based on voltage. Now let's move on to our final topic.
Right.
What happens when we start connecting inductors and capacitors together in series and parallel?
This is where things get even more interesting. Just like with resistors, we can often simplify circuits containing multiple inductors or capacitors connected in series or parallel into a single equivalent element.
Okay, so it's like finding the net effect of having multiple inductors or capacitors combined in a specific way. Let's start with inductors in series. What's the rule for finding the equivalent inductance when we have multiple inductors connected one after another?
Well, when inductors are in series, they all have the same current flowing through them. The total voltage across the entire series combination is simply the sum of the individual voltages across each inductor. If you work through the math, you'll find that the equivalent inductance of the whole series combination is just the sum of the individual inductances.
So it's just like adding up resistors in series.
Exactly. And any initial current present in the individual inductors will also be present in the equivalent inductor.
That's pretty straightforward. What about inductors in parallel?
When inductors are in parallel, they all share the same voltage across their terminals. The total current flowing into the parallel combination splits up among the individual inductors. The rule for parallel inductors is a bit different than for series. The reciprocal of the equivalent inductance is equal to the sum of the reciprocals of the individual inductances.
So it's like finding the equivalent resistance for resistors in parallel.
Exactly. And if each of the individual inductors has an initial current, the equivalent parallel inductor will have an initial current that's the sum of all those initial currents.
Okay, so parallel inductances combine like parallel resistances. What about capacitors in series?
For capacitors in series, the rule is similar to parallel inductors. The reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. And if each capacitor in series has an initial voltage across it, the total initial voltage across the equivalent capacitor will be the sum of those individual voltages.
Interesting. So capacitors in series combine like resistors in parallel. What about capacitors connected in parallel?
That's the simplest case. When capacitors are in parallel, they all share the same voltage, and the total equivalent capacitance is simply the sum of the individual capacitances.
So parallel capacitors are like series resistors. They just add up.
You got it. And if there's an initial voltage across the parallel combination, that same initial voltage will be present across the equivalent capacitance.
Great. So we've seen how to combine both inductors and capacitors in series and parallel, and we've drawn some interesting parallels to how resistors behave. This has been a really insightful deep dive.
I agree. Understanding these fundamental circuit elements is crucial for analyzing and designing more complex circuits. It's like learning the alphabet before you can read.
Absolutely. We've explored the core principles of inductors and capacitors, from their fundamental definitions to their energy storage properties and how they combine in circuits.
We've seen that inductors resist changes in current and behave like shorts in DC circuits, while capacitors resist changes in voltage and behave like opens in DC circuits.
And we've talked about how those energy storage properties can lead to some pretty interesting and useful behaviors.
I hope this deep dive has given you a solid foundation for exploring these concepts further. Think about how those energy storage properties of inductors and capacitors might be used in everyday technologies beyond the touchscreens we discussed. It's a fascinating area with endless possibilities.
Thanks for joining us for another deep dive. We appreciate you tuning in, and we'll see you next time.